Like as a phase transition between the water ice vapors in the statistical physics. Also, there are many phase transitions in the particle physics, especially the standard model. The one example is electroweak symmetry breaking, and the other one is QCD, so-called chiral perturbation theory. We can draw the phase diagram for the QCD over the two parameters. The one is the temperature T, represents the energy scale, and the other one is the baryon chemical potential, which corresponds to the number density of the baryon. And the chiral perturbation theory described how the precorcus becomes a bound state in the low energy scale. The typical QCD scale is given by the 100 mega electron volt, and especially the such QCD phase transitions that occurs in the early universe by the cooling of the temperatures. And we know that in the early universe the temperature is very high, so by the universe expansions the temperature becomes smaller, and QCD turn to the precork state to the some baryonic state or meson. This is called the hadron as a bound state. And the baryon chemical potential is known as smaller than the critical one, so the early universe got the second order or crossover phase transition, not the burst order phase transitions. So the precork bounds, so it composes a hadron. But in the large baryon chemical potential in the x-axis, such a quark gluon plasma QCP can support the burst of the phase transition over some specific critical point. The example of such a burst of the phase transitions of the QCD ones is some nuclei and some neutron star and color superconductors. When the temperature is small and the large baryon chemical potential, the phase, such a phase called the color superconductor, it corresponds to the low energy scale and the very dense material. So here's the four phases. In the high temperatures, low chemical potential, this corresponds to the early universe, and the other one, some artificial situation is the heavy ion collisions at LHC or RHIC. And in the small chemical potential, when the temperatures cool down, so smoothly crossover cycle in the low temperature regime. So by the chiral perturbation theory, there is a quark and antiquark condensate, and the hadron like as a meson and baryon stays arise. But in the high temperatures, the high chemical potential, the situations are different. In high temperatures and high chemical potentials, QCD behaves like the quark gluon plasma. But in the such low temperatures and high chemical potentials, such an environment is given by the neutron star core or core dense clear matter. This corresponds to the color superconductor. Like as an electron in the superconductors in the solid state physics, the quark can compose the Cooper pair in the size of the neutron star, especially the core. This is still hypothesis, but quite reasonable and possible. So, and the still the unknown and the mystery in the QCD phase diagram is the existence and the locations of the critical endpoint, the CEP, or the pulse of the phase transition. The specific values of the temperatures and chemical potential is not yet established. Because such at the large chemical potential, the calculations on the lattice QCD technique is very hard due to the sign problem. In the path integral, there's a no positive probability in the large chemical potential. The determinant for such a non-zero chemical potential is complex, this yield a negative probability. And the latest QCD, so the only values in the low chemical potential. So we don't know the exact locations of the CP. Many collider like as RHIC and the Bell try to search such a CP. Now, in the remaining time, I will talk about some of the few remarks on the QCD phase diagram. There is also the deformant transition from the isolated color charges to the high TC and high chemical potential, so called QCD. This is called some specific transitions, regions over the parameter space. And the crossovers are different to the second phase transition. In the second sort of phase transition, all the parameters are smooth, but there are still divergent quantity like the correlation length around the some specific transitions temperatures. But in the crossover case, all derivatives are smooth, so they're different. And if there is also the phase transition for the QCD, then the gravitational waves are expected, but this is not standard one. So if there is also the phase transitions from the color superconducting phase in the neutron star, then such gravitational waves can be generated from the mergers of the neutron star. And in the theoretical point of view, the lattice QCD is the one technique to calculate some specific system composed by the quark or the hadron. Because the below the QCD scale, the coupling constant, so rather than the one, this is called the color confinement due to the negative beta functions, including the loop contribution. In this, another scale is called the chiral perturbation theory. The opposite limit in the high energy limit, the coupling constants become small due to the quark and anti-quark dipole moment in the vacuum polarization. So the coupling constants become small. This corresponds to the quark plasma in the higher scale and small distance. So such a large coupling, strong coupling in the QCD in the lower scale makes the perturbate methods becomes impossible. So we choose parallel the non-perturbative methods like the lattice QCD assuming the finite space-time. But the problem is already I mentioned the lattice QCD does not work in the high chemical potential due to the sign problems of the path integral. In the phenomenological point of view, especially the experiment, the heavy ion collider can scan the QCD phase diagram, especially the relativistic limit. The accelerating nuclei is like there's a A or PB. If they collide each other in the LHC or relativistic heavy ion collider RHIC, then we can scan the QCD phase diagram. LHC and the top are linked target to the high energy, but the leak beam energy scans the BS and the pair target to the low energy but the high chemical potential. So the related observable in the such heavy ion experiment is the fluid behavior of the QCP or hadron jet by the quark or the baryon collisions, or fluctuations of the conjugate charge like the baryon number charge or strangeness of the quark, or dilepton signal productions. By these observations, we can scan and test the parameter space for the QCD phase diagram. And I will talk about some color superconducting pieces. Like as the electron, quark can have the quark attractive interactions around the baryon level at the dense material. The high chemical potential may be and the many quark situation. Then the quark forms a Cooper pair and the non-jealous energy gap, and this makes the massive gluon like as the massive photon in the solid state physics. In the color superconducting phase, there are also the two distinct phases. The one is the two fibers SC phase. There's only the up and down quarks that contributes because they are strong I mean the strangest quark is a 2-habit. Also there's a color variable locked by this. All the up-down strange quarks contributes in the very high chemical potential limit. In this case, the color and the variable is locked down. Such a color conducting phase can be possible in some specific situations, especially the complex and the dense materials. The one example is the neutron star is very cold, so low temperatures, but the materials are very dense and at its core. So the such as superconducting color phase is possible. Also, the other one, the nuclear methods. The idealized and the uniform nuclear system. There's no Coulomb-Sirk in here. In this case, there are liquid gas transitions to the nuclear. In the low maybe the materials are diluted, so that this is given by the gas. But when the maybe go to the large limit, material become denser, and the nuclear matters that transited from the gas to the liquid in the low temperatures. In the future of the cosmological point, the baryon symmetry of the universe is defined by the baryon numbers of the entropy density around to the 10 to the minus 10 number. This implies that the chemical potential is small compared to the universe temperature. This means that such a small baryon numbers baryon symmetry of the universe compared to the photon number. Here is the entropy number density, but we can recalculate with the photon number density. Such a small chemical potential means that the early universe QCD phase transition is the not part of the phase transition in the standard one. This is the crossover from the quark-gluon plasma to the chiral perturbation theory. But this is the standard scenario, but in the beyond standard models like the new physics, the non-standard QCD like the process of the phase transition is possible. Such a process of the phase transition is associated with the baryon analysis model and can generate the gravitational wave as a signal. So today we talk about the QCD phase diagrams as the two parameters, temperatures and the chemical potential. In the cosmological point of view, the standard one is just the crossover, but in the low chemical potentials with the dense material, there might be the process of phase transitions, but the locations of the critical point for the point for the process of the phase transition is still not unknown due to the sign problems of the lattice QCD. And also the low temperatures and high chemical potential limit. There is a color superconducting phase, which is possible in the cores of the nucleus, neutron star or nucleus matter.